here in Ocho Rios, getting ready for another math lesson. Go ahead and pull out your packets and get ready to take some notes. We're going to go ahead and jump into the video. So we are here for lesson 4-4, constructing exponential equations. Our learning target today is that I can write an exponential equation to model a given situation. So we're going to go ahead and look at the standard form for an exponential function. And the general form for an exponential function is going to look like we have on the screen here. Y equals a times b raised to the x power. We get the name exponential because our x, or our input value, is in the exponent. Alright, so x is still going to be our input, and just like we've done in all our other functions, y is still going to be our output. Looking at the values a and b, a is going to be our starting value for exponential functions, and b is going to be what we call our growth factor. So this is the overall general form for an exponential function. We are going to take a look at a couple different variations of this in future lessons, specifically for compound interest and exponential growth and decay, but they're all going to stem from this original equation here. So make sure you have those boxes labeled. And just a technicality to point out, this only works when a is not equal to 0, b is not equal to 1, and b is greater than 0. Otherwise, this is going to be a little bit different. It's going to alter the form of our formula, and it won't be a true exponential anymore. Alright, so let's look at example 1. The function f of x is equal to 2 times 3 raised to the x models an insect population after x days. We want to know what will the population be on the 5th day. So if we look at this function that we are given, f of x is equal to 2 times 3 raised to the x power. If we break this down like we had before, x is still going to be our input. Now notice that instead of y we are given f of x. This is function notation, but this is still going to be our output. A value of 2 here, where a is, means that we are starting with 2 insects. That's our start value. And then the 3 is going to be our growth factor. That means that our population is tripling each time, since it is a 3. So now when we want to actually find what they're asking us to figure out here, we want to know the population on the 5th day. 5 is going to be our input because that's how many days we want to evaluate this function for. So we're just going to plug in f of x is equal to 2 times 3 raised to the x power. X is our input, so we are going to replace that with 5. So now all we have to do is plug this into our calculator. We can plug this in all at once, or we can plug it in a little bit at a time. If we were to plug in each part a little at a time following the order of operations, we would have to do the 3 raised to the 5th power first, which is going to give us 243. And then when we multiply that by 2, we're going to get that we are going to have 486 insects. Now, of course, you could have plugged that all in from the beginning in your calculator, but if you're doing it and breaking it down step by step, you could do it like this. Otherwise, you can just plug all that into your calculator at once. Just be careful putting in your exponent, and you will get 486 insects either way. Alright, so now looking at telling whether or not something is an exponential function. Remember that when we were looking at linear functions, or straight lines, we always saw a constant rate of change. However, when we have an exponential relationship, we will not have a constant slope. And that's why we keep saying the average rate of change instead of just the rate of change or the slope for exponential functions. Instead of having an average rate of change, they'll have an average ratio. So that means we're going to be multiplying, just like in our geometric sequences at the beginning of this unit. So we're going to go through a test to tell whether a set of ordered pairs could represent an exponential function or not. And we're going to be able to give evidence to support our answer. So the first thing we're going to need to do is we're going to need to look at the y values that we're given and the x values we're given. We want to make sure that we're going up by even steps. That way we know that we have a ratio that's going to be consistent away. So we're going -1, 0, 1, 2 in our x values. So we can see that those are going in order. Now, what we're going to want to do is subtract our y values. So we would do 3 minus 1.5, and we would get 1.5. Then we want to do the next two y values, 6 minus 3, and we're going to get 3. And then we do the next two, 12 minus 6, and we're going to get 6. Now recall, if this was a linear function, these should have all come out to be the same. We should have been increasing by the same amount each time. What we are going to actually test is to see if they have a common ratio. And to do that, we're going to take these numbers right here that we just got from doing our subtraction, and we're going to divide by the previous term to see if we should get the same thing. If we do, we're going to have a constant ratio, and it will be exponential. If not, then it's not going to be an exponential function. So I'm just going to take my two values here, 3 divided by 1.5. Alright, and I'm going to do these two values, 6 divided by 3. So 3 divided by 1.5 is going to give us 2. And 6 divided by 3 is going to give us 2. Since we got 2 when we divided on both of these, we got a common ratio of 2. So we are going to be able to say yes, that this is an exponential function because we have a common ratio of 2. Alright, so we're going to take a look at example 3. Example 3 is very similar to example 2. The only difference is instead of giving the ordered pairs listed out, we are given to the ordered pairs in a table. We're still going to follow the same process. We still want to subtract and find the difference between the two y values first. 11 minus 21 is going to give us a negative 10. 6 minus 11 is going to give us a negative 5. And 3.5 minus 6 is going to give us a negative 2.5. So what we need to do now is divide these differences and see if we get a common ratio. So negative 5 divided by negative 10 is going to give us 1/2. And negative 2.5 divided by negative 5 is going to give us 1/2. So since we have a common ratio of 1/2, we are going to see that this is an exponential function. If these were to come out to be two different numbers, let's say 1/2 and 1/4, then we would say that this is not an exponential function. Alright, let's move on to our final example. Our final example is a half-life problem. You may have seen these before in science class. Just to give you a short summary of what a half-life is, a half-life is how long it takes for half of a radioactive material to decay. So, the half-life of zinc-71 is 2.4 minutes. If the sample started with 100 grams at the beginning, we want to know how many grams would be left after 7.2 minutes had elapsed. So let's recall our general form for an exponential function. It is y equals a times b raised to the x power. And let's pull out what information we can use from this. Remember, our a is our starting value. So that's going to be how much of the sample we are left with, or we are beginning with rather. In this case, it would be 100 grams. So our a value is going to be 100. Remember, b is our growth factor. Now, when I was summarizing what half-life was, we said it was how long it takes half the material to decay. So what our growth factor is going to be in every single half-life problem is going to be 1/2. So b will always be 1/2 in a half-life problem. Let me say that one more time. On a half-life problem, our b value will always be 1/2. Now x is going to be a little bit trickier. X is our input, remember. And we need to put in how many half-lives we're going to have. Now, the problem doesn't come straight out and tell us how many half-lives we're given. Instead, it gives us how much time a half-life is and how much time has passed. So what we're going to have to do is calculate how many half-lives we went through, given the information we were given. So we know that 7.2 minutes elapsed, and we know that it takes 2.4 minutes for a sample to decay. So what we have to do is divide 7.2 by 2.4, and that's going to give us that we are looking at 3 half-lives. So 3 is going to be what we're plugging in for x. So now putting that all in together, remember our starting value was 100. Our growth factor will always be 1/2 for a half-life problem. And we know that we are looking at 3 half-lives. That's how many half-lives occurred in 7.2 minutes. So again, we type this into our calculator, and we go ahead and evaluate this. And we're going to find that we have 12.5 grams remaining. Alright, just one final reminder to make sure that this is stuck with you. In a half-life problem, B will always equal 1/2 in our half-life problems. Alright, that wraps up your lesson 4-4. There is no application for lesson 4-4. However, while you're working on the practice, you may want to check out a supplemental video that we have uploaded beneath this video, that might give you a little bit extra guidance on that practice. Alright, see you guys next time.